Hi everybody, so in this lesson we're going to use the sampling distributions which we talked about in the previous lesson to make some inferences, to make some predictions, some guesses. So the weight of let's review what we did in the beginning of the statistics unit here. So the weight of potato chips in a medium-sized bag is stated to be 10 ounces. The amount that the packing machine puts into these bags is believed to be normally distributed with a mean of 10.2 and a standard deviation of 0.12. What is the probability that a randomly selected bag of chips is underweight, below 10 ounces? So this is what we did in lessons 1 and 2 of this unit, is we drew our normal curve, and we said, okay, my center here is 10.2, and I have a standard deviation of 0.12. And I want to know what's the probability I'm 10, which is below average, or under that, what proportion, what percent of the bags are underweight? So what's the probability that of any bag I pick weighs less than 10 ounces? Well, the way that we did that is we found a z-score. How do I find a z-score? Well, it's the value minus the mean in terms of standard deviation. So my z-score is what I really need to find here. What is the probability that I'm less than 10? Well, I'm really going to find the probability my z-score is smaller than, well, let's see what it is. Value minus mean, enter, divided by standard deviations. How many standard deviations am I from the mean? So negative 1.66666666667. So negative 1.67, I'll say. What is the probability my z-score is less than negative 1.67? Well, the way that we do that is we go to second distributions, second vars, normal CDF, and now we have to use our picture here. How low do I go? How far left do I shade? Well, I shade down to negative infinity. So negative a bajillion. How far up do I go? Well, that's why we found the z-score. That's what 10 became. We standardized that number 10 so that we could use our calculator, negative 1.6666667. And then this gives me the probability. What's the probability here? 0.0478. 0.0 equals 0.0478. So about 4.78% of the bags of chips are underweight. What a shame. They're lying to us here. They're telling me I'm getting 10 ounces of chips, but there's a 4.78% chance I have less than 10 ounces of chips in my bag. That's what we did in lessons 1 and 2. So here's where sampling distributions come into play. What is the probability that a sample of 8 bags of chips has an average weight that is below 10? So notice I have a sample of 8 chips, and I want to know the probability that my x bar, my sample mean, is less than 10. So we do the same game, except we're not using this normal curve. I'm sampling 8 bags of chips at once. I'm using a sampling distribution here. So be careful. The central limit theorem tells us our sampling distribution is normally distributed. The center is the same, so the center is still 10.2. But remember, we have those two standard deviation formulas that I want you to write at the top of your paper. The two formulas for if I'm working with a sample mean, it's standard deviation over the square root of n. And if you're working with a sample proportion, it's the proportion times 1 minus the proportion over n. Those are our two formulas for working with this with sampling distributions. This is when I work with x bars. This is when I work with p hats. So in this case, this distribution of averages here has a standard deviation of, well, 0.12 over the square root of 8. I have a new standard deviation there. And everything else is now the same. What's the probability I'm less than 10? Well, I find a z-score. Value minus mean. In terms of, this number is different though. In terms of standard deviation. So we got to be careful when we type this in. We got to do value minus mean divided by parentheses, or maybe use the fraction button, 0.12 divided by the square root of 8. So notice you got to use parentheses when you're dividing by that new standard deviation, that new standard error of my sampling distribution. Oh goodness, that's completely unlikely. So negative 4.714 is my z-score. So this is negative 4.714, I think I said. So now I want to know what's the probability my z-score is less than that. And I can tell you right now the answer is going to basically be 0. So second normal CDF, lower bound, how low do I go? Negative infinity, all the way up until my z-score. All the way up until negative 714. What does that probability come out to be? What does this mean here? Your calculator does this, and by 11th grade, you should know what your calculator is telling you. It's 1.2 times 10 to the negative 6. 1.2 times 10 to the negative 6, which is 0.0000012. That's the probability of me getting an average less than 10. If I get 8 bags of chips, what's the probability that average is underweight? It basically never happens. This basically never happens. So that's the nice thing, is what this sampling distribution told us. What's the probability I take 8 bags of chips and the average of those bags of chips is underweight? It's basically 0. This event basically never occurs. This event basically never occurs. Never occurs. That's the nice part. But what I need you to understand is here, I was just picking one chip, one bag of chips. Here, I was working with a sample mean. I was working with an average. I was working with an X bar, so my standard deviation formula had to change. Because this right here is a sampling distribution. This is a sampling distribution of sample means, of X bars. Whereas this is just working with bags of chips. Down here, I'm working with X bars. I'm working with means. That's the fine distinction here. Number 2 says, assume that 30% of students at a university wear contact lenses. So this is our assumption. We're assuming the parameter is 30%. We're making that assumption about this college, that the parameter is 30%. So a random sample of 100 students from this university is chosen. What is the probability that 33% of students in this sample wear glasses? So we want to know here, what is the probability that my p-hat is greater than or equal to 33%? What's the probability that my p-hat is greater than or equal to 0.33? Now, why do we do greater than 0.33? Well, because if you're 34%, you've met the 33% wearing glasses. So that's why we do 33 or greater. So this is a sampling distribution. From my university, I'm sampling 100 students. So the central limit theorem tells us it's going to be approximately normal. What did we assume the center was? We assumed our parameter was 30%. And I want to know what's the probability I get 0.33 or higher. So this is what I'm shading here. So the way that we do that is we find a z-score. Well, the key thing is, what's my standard deviation? So this is that weird p1 minus p over n formula. So the way that we find our standard deviation, the way that we find sigma here, is we take the square root of what's our true parameter, 0.30, 1 minus 0.30 over my sample size, p, 1 minus p over n. That's how we compute the standard deviation for this normal curve. So when I get my z-score here, I want to do 0.33 minus 0.30 in terms of how many standard deviations am I above the mean. How many standard deviations am I above the mean? So I'm going to go to my calculator. 0.33 minus 0.30 divided by the square root of a fraction. What was that fraction? 0.3 times, or parentheses, 1 minus 0.3 over the sample size, which was 100. So I found the difference divided by the standard deviation. And this is going to give me a z-score. I have a z-score of 0.655. So my z-score is 0.655. And if I look at that, that's my lower, and I want to go up. So my lower, so when I go second distributions, normal CDF, my lower is 0.655, and my upper bound is going to be a majillion. So the probability is 0.256. So this equals 0.256, or about 25.6%. So this isn't unusual. Getting a p-hat of 0.33, assuming the true proportion is 30%, isn't unusual. This value, this sample proportion, this p-hat is not unusual for assuming that that population parameter of 30% is not unusual. It's not an unusual sample statistic. It could happen by chance. This can happen by chance. This can happen by chance. It's nothing special. It's not an unusual value for a p-hat given these scenarios. So I drew my normal curve. You're going to have to somehow find the standard deviation, and it's going to be one of these two formulas. Standard deviation over radical n for means, or if I'm working with proportions, it's p1 minus p over n, all that's square rooted. Got a couple more, we'll call it a lesson. So in 2004, the National College freshman to sophomore retention rate held steady at 74%. Does a college where 522 of the 603 freshmen return the next year as sophomore have a right to brag about an unusually high retention rate? So does a college that has, well, what's our p-hat here? What's our p-hat? Their sample was 522 out of 603. So their p-hat, let's just get the value of that, 522 out of 603. Their sample proportion, wow, they had 0.866, let's say. They said they had 86.6% of their freshmen return. So let's assume that this is the true value. Let's assume that this is the parameter. Let's assume that that's the parameter. Let's see how extreme this p-hat is. So let's draw our normal curve. The center is going to be 74%. I'm all the way over here at 0.866, and I want to know what's the probability that I'm that extreme. Is that an extreme probability? Well, I need my standard deviation. And the way that I get my standard deviation is the square root of the proportion, the parameter, 1 minus the parameter, over the sample size. How many freshmen did I sample? 603. That's my standard deviation. So now I can find the z-score. Z equals value minus the mean in terms of standard deviation. And I just have to throw this in my calculator now. So that value minus the mean, minus the center, divided by, well, what was my standard deviation? Well, it's the square root of 70, I need a fraction, sorry. Alpha y equals enter, 0.74, parentheses, 1 minus 0.74, all over 603, I believe it was, enter. Ouch. That has a z-score of 7.035. That gives me a z-score of 7.035. Which now I can find that probability. So that's my lower bound, and I'm going to go all the way up to infinity. So second distribution, normal CDF, 0.35, going up to a bajillion. What's that probability come out to be? Well, I see this e to the negative 12 again. So what that means is the probability of this happening, the probability that z is bigger than 7.035 equals 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. That's the probability. 1 times 10 to the negative 12, which is basically equal to 0. So did this happen by chance? No, this college definitely has something to brag about. This college is very extreme. This sample proportion, this p-hat is very unusual. Very unusual. It's very extreme. So does this college have something to brag about? Absolutely they do. Their sample proportion of freshmen who stay over is very, very high compared to the national average. This sample proportion is extremely rare if that's the national average. So this college does have something to brag about. So the steps are the same. Draw your normal curve, like the central limit theorem tells us. Label the center. Label your sample statistic. Shade into the tail, and then you find the standard deviation. Z-score, normal CDF. You got a lot of steps for these questions. These questions are not fast. So when flipping a coin 100 times, you got 61 tails and 39 heads. We're assuming this coin is fair. So we're assuming the true parameter is 50%. We're assuming that the proportion is 50%. What is the probability of obtaining 39 heads out of 100? So what's the probability of getting a p hat? Well, let's see this. So here's 50%. I'm all the way here at 39 or less. What's the probability that I get a p hat less than or equal to 39? Right? That's my sample proportion, 39 out of 100. How extreme is this p hat? Can it happen by sampling variability? Or maybe my coin's not fair. Maybe something's going on here. So let's find this probability. Well, we need a standard deviation. Our standard deviation is, well, we use the population proportion. P 1 minus P over how many flips? 100. So it's the square root of P 1 minus P over N. So now I can find a z-score. Z equals value minus mean divided by the standard deviation, which is this crazy number here. So let's type this on in now. 0.39 minus 0.50, enter, divided by the square root of, I need a fraction, P, parentheses 1 minus P, all over the sample size was 100 coin flips. So I get a z-score of negative 2.2. Z equals negative 2.2. So what's the probability that my z value is less than negative 2.2? What's the probability z is smaller than negative 2.2? Well, distribution, second vars, normal CDF. Let's look at our picture. Lower bound, I'm going down to infinity forever. Negative infinity. And then my upper bound was negative 2.2. So this happens 0.0139. This happens 0.0139, which is about 1.39%. So because we're going to say this is unusual, it can happen. It can happen that I get 39 heads out of 100, but I'm going to say this is an unusual value. This isn't unusual. This isn't extreme. This is an unusual event. The cutoff is 5%. If something happens more than 5%, I'm going to say it could happen by chance. It just happened. It maybe it's not what I expected it to be, but it's 5%. That's a likely occurrence. Something that happens less than 5%, less than 5% is the key thing here. Something that happens less than 5%, I'm going to say it's an unusual event. So this p hat here, this is an extreme p hat. This is an extreme sample proportion. This p hat is extreme. So do we have evidence that our coin is not fair? We do. Because we got an unusual p hat, it probably didn't come from a fair coin, a 50-50 coin. This is extreme. So we have statistical evidence. We have statistical evidence that our coin is not fair. Go away. That our coin is not fair. Why? Because the probability of getting a sample proportion this extreme or more extreme happens about 1.4% of the time. That's pretty unusual. So I'm going to reject this assumption that I had a fair coin. We have evidence that this p hat is extreme. So it seemed like it could have happened by chance, but I'm going to reject that because it happens less than 5% of the time. One more problem and we'll call it a day here. So in 2019, the average score on the AP Statistics exam was 2.85 and the standard deviation was 1.33. At CCHS, 44 students took the AP Stats exam and earned an average score of 3.05. What is the probability that 44 randomly selected students' average on the AP Stats exam is better than Cornwall's average? So what's the probability that my sample mean is bigger than 3.05? That's what I want to know here. What's the probability if I randomly select 44 students that my sample mean is bigger than CCHS? What's the probability that someone does better than Cornwall? So this is a sampling distribution because I'm taking a sample of 44 students. So I'm going to have a normal curve. The center is the true center, so 2.85. But the standard deviation changes. Remember, the standard deviation, we're not dealing with proportions here. So this is the sigma over radical n, 1.33 over the square root of 44. So it's the original standard deviation divided by the square root of the sample size. That's how we compute the standard deviation of our sampling distribution here. So our sample mean is up here at 3.05. There's Cornwall. What's the chance I do better than Cornwall is my question. So let's find a z-score for Cornwall. Cornwall is value minus mean in terms of standard deviations. How many standard deviations am I from the mean? So let's get the z-score. 3.05 minus 2.85 divided by, use parentheses here, the original standard deviation, not two parentheses, just one, 1.33 divided by the square root of, what's my sample size? 44 divided by the square root of 44. Close it and enter. That's my z-score. My z-score is 0.997. So what's the probability? So I'm down here at 0.997 or all the way up to infinity. What's the probability that z is bigger than 0.997? So let's see what that is. Second distribution, normal CDF, 0.997, all the way up to, that should be 0. All the way, my upper bound is infinity, a bajillion. So the probability that someone's average is better, so randomly selecting 44 kids and doing better than Cornwall, that happens 15.9. So that happens 0.159 or 15.9% of the time. So the probability that 44 randomly selected AP Stats kids do better than Cornwall's average, do better than CCHS's average, is only 15.9%. Now, it's not unusual, but it's not an unusual outcome. We don't have evidence to say that Cornwall's scores are really, really good and really, really high and really above average. But we do have that. What we're saying here is that the probability that someone does better than Cornwall's 44 students, a random sample of 44 kids does better than our 44 kids, it happens about 16% of the time. So we did much better than other schools based on our average and compared to their average. So this is how sampling distributions work. The first thing you do is you draw your normal curve. You draw your normal curve and label the center. Label the center with the true value, with the parameter that we think the parameter is. Then we compute this new standard deviation. How do we compute it? It's the original standard deviation over radical n, or it's the square root of p, 1 minus p over n. That's theoretically what our sampling distribution standard deviation should be. Then you find a z-score, and then you normal CDF. Then you use the normal cumulative density function there. So that's our steps. Draw our normal curve, compute the standard deviation for the sample mean or the sample proportion, because that's what we're working with here. We're working with a sample mean or a sample proportion. You find a z-score, and then you do a little normal CDF. So that's how sampling distributions work. And I'll see you guys next week when we talk about confidence intervals.